This video is about energy levels in an atom. We'll start by learning about energy level basics, and then we'll discuss transitions between energy levels. Let's see the basics. We learned earlier that atoms consist of a positively charged nucleus and negatively charged electrons. The nucleus itself is composed of positively charged protons and, except for a few cases, uncharged neutrons. To learn about energy level basics, we'll use the planetary model of the atom. In this model, electrons orbit the nucleus, similarly to how planets orbit the Sun. Of course, this is a simplified model with circular orbits. However, it will help us get a good grasp of energy level basics. Now, just as planets around the Sun are in different orbits, electrons can be in different orbits around the nucleus. These orbits are also called energy levels. In different orbits, or in other words, at different energy levels, electrons have different amounts of energy. We'll now move on to examine the energy levels in a hydrogen atom, which is the simplest atom, as it is composed of one proton and one electron. One way to show these energy levels is through a diagram like this. The black dot represents the nucleus, and the dashed circles represent the 5 energy levels that we find in a hydrogen atom. The energy levels are simply named as first, second, third, fourth, and fifth energy level. Even though we often think about energy levels as orbits, these energy levels are usually represented by a set of horizontal lines like this. The levels are labeled as n equals 1, n equals 2, n equals 3, and so on. Now, as we mentioned earlier, at different energy levels, electrons have different amounts of energy. Let's add the specific energy values for the hydrogen atom. As you can see, since we are dealing with very small amounts of energy, the values are given in electron volts. The energy level where n is equal to 1 is often called the ground state. When an electron moves from the ground state to a higher energy level, we say that the atom is in an excited state. Therefore, the second energy level is often called the first excited state, the third energy level the second excited state, and so on. An extremely important point is that electrons have to be at one of these energy levels, therefore they must have the specific amount of energy of the given level. This means that energy levels in an atom are quantized. Put slightly differently, if you examine an electron in a hydrogen atom, it will always have one of the 5 energy values that you see here. You will never find an electron with an energy of, for example, negative 10 electron volts. Or if you do, you can probably claim the Nobel Prize in Physics. Next, we'll move on to learn how electrons transition between these energy levels. Let's return to the hydrogen atom energy level diagram. When transitioning, electrons can move from a lower to a higher, or from a higher to a lower energy level. More about this in the next 2 videos. To show transitions on the diagram, we use arrows. So for example, a transition from the first energy level, so from the ground state, to the third energy level, so to the second excited state, can be shown like this. Here is an example of a transition from a higher to a lower energy level. Most likely you have already noticed that energy values on this diagram are negative. This is so because electrons must receive energy in order to move from a lower to a higher energy level. Another important point is that in order for an electron to move to a higher energy level, energy must be transferred to the electron in one discrete amount. This is so because, as we said earlier, energy levels in an atom are quantized. As an example, let's take a transition from the first energy level to the second energy level. The difference between these 2 energy levels is 13.58 minus 3.39 electron volts, so 10.19 electron volts. So if we want an electron to transition from the first to the second energy level, we need to supply the 10.19 electron volts all in one go. If we try to supply this energy in 2 or more installments, so for example first 8 electron volts and then 2.19 electron volts, the transition will not happen. In a moment, we'll explore this concept further through an example. The energy that causes an electron to move from a lower to a higher energy level is transferred to the electron when the atom absorbs electromagnetic radiation. An interesting property of electromagnetic radiation, so for example visible light, is its wave-particle duality. If you take higher level physics, you'll learn more about this property in subtopic E.1.3, but for our purposes here, we'll simply say that electromagnetic radiation is composed of particles called photons, and that these photons carry a certain amount of energy. Now, the energy of a photon depends on the frequency of the electromagnetic radiation. The following formula shows the relationship between the energy and the frequency of a photon. Here E is the energy of the photon, h is Planck's constant, and f is the frequency of the photon. Let's now work through an example that involves this formula and the energy level diagram on the left-hand side. Take a moment to pause the video and read this example. The transition from the ground state to the second excited state is shown by the blue arrow on the diagram. Let's start by finding the energy that we need to supply to the electron in order for this transition to happen. To do this, we need to find the difference between the two energy values, which gives us that this energy is equal to negative 1.51 minus negative 13.58 electron volts. The result of this calculation is 12.07 electron volts. As we mentioned, an energy level transition takes place when an atom absorbs electromagnetic radiation, in other words, when it absorbs a photon. So in order for the specific transition to take place in our example, the photon that is absorbed by the atom must carry exactly 12.07 electron volts of energy. Now to calculate the frequency of this photon, so the frequency of the electromagnetic radiation, we can rearrange our formula to get that F is equal to E over h. A common mistake that people make in this calculation is that they forget to convert the energy value from electron volts to joules. To make this conversion, we need to multiply the electron volt value, so 12.07, by 1.6 times 10 to the power of negative 19, which is the value of the elementary charge, so the charge of an electron. This is then divided by Planck's constant, so by 6.63 times 10 to the power of negative 34. The result of this calculation is approximately 2.91 times 10 to the power of 15 Hz. Based on its frequency, we can of course calculate the wavelength of the electromagnetic radiation. We just need to use the wave speed equation, which, after rearranging, gives us that lambda is equal to c over f. I'm using c for the speed of electromagnetic radiation, so the speed of light in vacuum. Substituting, we get 3 times 10 to the power of 8 divided by 2.91 times 10 to the power of 15. Carrying out the calculation, we get approximately 1.03 times 10 to the power of negative 7 meter, which can also be written as 103 nanometers. With this example, we have completed our video about energy levels in an atom.